So I am David Aronchick. I'm here to talk to you about transforming data through open compute. So, one of the things I actually saw a funny thing. I meant to drop it in the slide deck. Every slide deck in big data in the past 10 years basically looks like an angle up to the right of infinite data in the future, bigger than we even have today. And it's true. Data is growing at an absurdly fast rate. But the problem is like, how do we make that data available? It can't just be throw it up on an FTP site and hope that it works. You see slides like this all the time. Big data will affect every industry in some regard. But when you think about how people are actually engaging with it, it looks like this, right? Very often you will see data projects fail at greater than 50% of the time. To some degree, like not doing any work is better than what they actually did. It's a coin flip to see whether or not it pays off. And so one of the things that we started to think about when we got underway with this project was really how to make making use of the data easier. Well, to step back, we had to look at what it meant to run a data pipeline and what the biggest pain points people were having when it came to these things today. And we thought that it's really broken down into these three big categories. The first is around familiarity. So first, if you think about what data pipelines look like today, and I would argue that every time you engage with data at all, you are engaging in a pipeline of some way. A lot of people think about it like this. I'm just going to go out and build a model or do an analysis or whatever it might be. But anyone who's actually engaged with a data pipeline knows that it actually looks like this. It's many, many steps tied together with many different components of functionality, where that building a model is just one element of it. And oftentimes, it's not even the step that is the problem. It's the interconnectivity between those steps. And that results in an enormous amount of challenge on how to actually build these things and make them reliable. Because when step number 9 is the one that fails, but everything else works, how do you figure out it was step number 9? How do you debug it? How do you rewind it back to the beginning and replay it without taking months and months to do the entire thing? And to show you what this looks like in the real world, this is a study that came out of Microsoft, one of the most sophisticated data organizations in the world, and they did a survey across all of their internal folks. So this is internal Microsoft stuff, and they found over 158 different tools in use. So every one of those boxes that you saw there, people are using whatever is familiar to them. And if you try to adapt and say like, oh no, everyone's got to port to this other thing, you're going to have a bunch of very unhappy people. And we haven't even gotten to data platforms yet, right? We're just talking about the tools that people are actually using to build these things. When you think about compute providers, you might have something along these lines. And then when you think about data providers, you think about things like this. On the left-hand side, it could be containers, it could be Swarm, it could be some other kind of like distributed job orchestrator. It could be Web 1, Web 2, Web 3, raw VMs, who knows. On the data side, you have open source projects, you have closed source projects, you have MPI, high performance compute, each time something very, very different. And the problem is that we're asking our data scientists to make a decision here. Or we are forcing them into very constrained locations and say like, look, I know that this thing worked great for you in your local Jupyter notebook, but now I'd like you to completely change the platform that you're executing on and help me debug this massive platform over here. So that's generally going to be a bad time. To extend that, we get to simplified, right? And the summary here is pretty straightforward. When you think about what it takes to build this, let's look at what it takes to build the hello world equivalent for data pipelines, right? The housing price example, where you build a model using nothing more than pandas to do a regression and determine what an average correlation between, I think it's square foot and, or excuse me, zip code and price, right? That's it. It's a very hello world thing. It's about 3 lines of code. Is 2 if you get rid of the print statement. In order to do the exact same thing in Spark, it looks like this, right? And that's not even everything. That's like some of it. I couldn't even fit it all on the slide. And again, look at what we ask people to do, the data scientists. They have to figure out a brand new platform. They may not know Java. They have to figure out how to do this distributed execution and compute. They have to figure out how to debug it, what went wrong between that one line of code on the left and the actual thing that's out there running. And this is not to bang on Spark as being like somehow subpar. It's not. It's a phenomenal platform. But it is a big leap for a lot of people. And that's a big challenge. And that's going to slow people down. And to be clear, like you ask, well, what do they want? Well, my supposition is this. This is SED. SED was invented, what, 48 years ago? 49 now? I don't know what month it was, but let's call it 48 years to make the math easy. It is so widely used today, and yet we say, oh, you know that great tool that runs perfectly, that does exactly what you want at gigabyte, at terabyte scale? No, you can't use that. You got to use something else. That's a disaster. My proposal is we bring data science back to the 70s, right? And to be clear, it's not even just the data scientists, right? What does it look like to actually implement one of these data platforms or things like that, for your SREs? I ran this query the other day. I just put it out on Twitter. I said, here's a bunch of ideas of things that go wrong when you're building your data platforms. And this isn't even the entire list, right? It's a phenomenal number of things. And we're asking our SREs to take all of this on. Or it just doesn't work, and you have no idea why, right? For no discernible reason. So again, it's just complexity on top of complexity. You're virtually guaranteed that you're going to get less than 50% success rate when we're shoveling this stuff at people. So yes, what's one thing they can agree on? These things suck. And finally, we get to collaborative. So now we're in this brand new world where we're collecting more data than ever before and theoretically changing the universe with all this information. But we're asking people to do it over and over again. Here we are at a conference completely dedicated to open data, right? And there are amazing tools out there and data sets that are available on every cloud. AWS and Google and Azure and many other places have these open data sets that are available and cataloged and so on and so forth. But they're not terribly usable. Like more often than not, they just give you an FTP or a GitHub link or something like that, and they don't really tell you what to do. And the problem with that isn't that the download, which in and of itself is quite onerous, it's how much we're asking people to do over and over again with no collaboration. So here's an example. A very common open data set is what's called Landsat. This is in the US. They publish a very large data set. It's about 1.5 petabytes of satellite imagery on a regular basis, which is incredibly valuable. You can go and scan the entire world and do all kinds of interesting analysis against it. In this case, you have a number of different situations where someone will look at that data set and, you know what, that's not exactly the data set I'd like. I'd like to change it in the following way. So we have our data scientist number one. She wants it tiled. She wants to break it down into smaller sections. She just wants that local section in the middle there. Data scientist number two, she wants it scaled. Same thing, but reduced pixels to reduce the overall cost to train and move these things around. And data scientist number three, she might want it grayscale, which is actually a very common tool because it reduces the size so much, but you're still able to get objects and things out of it, which greatly increases the speed. So each one of these data scientists have now had to go off and do their own work in an isolated way. What if a data scientist came along and said she wanted to actually do all three, which is, again, a very common thing? Well, she can't merge them together. There's no origination. She has to go back to the original and do all three things in serial. That's a disaster as well. What would be ideal is we had some form of open compute where as you went through and executed all three of these jobs, you gave each one a unique identifier that said, hey, here is what I did with this job. Here's the code that I ran against it. I'm going to take that and republish it to the web. Or maybe you're just private and you republish it internally. You can do that too. And then when our data scientist comes along, she says, oh, look, there they all are out there. I'm able to choose the one that's the closest, extend that one instead of building it from scratch, or potentially merge them all together. And then when I'm done, I'm going to republish that as a summary as well. Now giving you lineage between these various elements. Again, truly transformative. And this is really only possible if we start to get to these open data concepts and open compute concepts. And one thing I do want to touch on with that is I keep saying the word open, open, open. And it really is that. But it's not necessarily meaning purely public data. Even within an organization, even within a single division, a group, you're going to want a way to share and use these concepts over and over again. You need a way to identify the work that has been done and allow the next person to come along, look at what was done before them, and make sense of it. So the summary of what we're trying to achieve here is familiar, simplified, and collaborative. What do we do to achieve that? And that's where we come to Project Bacalhau. So this is a project we launched in February of last year. It is completely open source. It is Apache and MIT licensed. We wrote our first line of code in February. We hit alpha in June. And in November, we had our first public summit called the Compute Over Data Summit, completely dedicated 2 days of talking about how we might transform the nature of these interactions. And our goal is pretty straightforward. We want to transform data processing by giving developers simple, low-cost, and distributed first tools that unlock this collaborative ecosystem. And one of those things I love to touch on there is that distributed first. There are many things that achieve things like this today. And we are very much building on the shoulders of giants. A lot of the team works on the team, myself included, were some of the earliest contributors to Kubernetes. And we think that that is a wonderful platform, and we are not supplanting it. What we are trying to do is augment these data pipelines in ways that make the overall process richer, more reliable. And when you get to use those more centralized platforms, you're able to do that at much greater speed and with much greater efficiency. The features that we already have look like this, and this is really just a subset. We already support 1,000 nodes, 10,000 jobs. We're able to do very large-scale processing. We support HTTP downloads and GPUs and all these various things. And for us, the most important thing is all of those elements before. Each of these are features, feeds, and speeds, and so on. But I can't stress enough, it is about making it simple and collaborative and familiar. So what does that look like? What can you do with it today? Well, how about run Python, right? Without doing anything, I just take my standard Python job and run it. You can see they're right there in line. I'm able to execute it. Or maybe I take an entire script and I execute that. Or maybe I build it into a container that I can use repeatedly in the same places that I would use other containers and run that. And presto, it just works. And here in the upper right-hand corner for all these slides, you'll see a QR code. That will link directly to the documentation that shows exactly how to do what you're seeing here. How about R? We support that too. You can do that right there in line, one line of code, run your R script, presto. How about pandas? You want to run pandas? No porting the entire thing to Java 6. You can just run it. This is, in this case, to show you how it's more complicated, you're able to take multiple files. So you'll have your CSV and potentially your Python script. You upload those both to IPFS or whatever store you would like, and then you're able to execute over multiple files. It's not just a single script that you're executing here. You're executing an entire context against those files. Just to show you, we're going to start getting more advanced here. DuckDB is tremendous. People are really enjoying how it's working, and it gives you arbitrary query semantics against files, in this case a Parquet file. And you're able just to execute SQL against it. And you're able to do it on a remote machine, potentially one that either doesn't have the data, or potentially one where you don't actually have the data locally, or maybe you don't have the necessary hardware, or you just want someone else to handle the job and run it. We do that too. How about YOLO? One of the most popular object detection algorithms, an entire model built into a container. Those weights are available for you. You're able to run them over thousands and thousands of images yourself and generate these kind of outputs of objects and object boxes in all those images. Now, I know you're a very demanding group of people. Let's get to the real stuff, right? How do you do stable diffusion? There you go. One command, that simple. Stick your prompt in, off you go. That's it. Seriously, that is it. There's no secret sauce here. Go create your nightmare fuel. And even further than that, you don't even have to install it. We even support running this directly in Colab. And again, I want to reiterate, this is an open source project, Apache 2, you can take it, you can run it, you can fork it, you can join our Slack channel and complain to the developers. This is about trying to transform the way that people engage with open compute. And we're trying to do that right now. And then we get to one of the most exciting features that we're proud to talk about. This is very early thinking, but we're really excited with the direction things are going, because we are talking to a number of people right now who are going to be able to use this open compute in a completely novel way. And the problem that people run into is what you see here. Let's say you have organization A and organization B. Very common situation where you don't want to necessarily share the entire security profile between those two people. It's very often that people will need to query between these two locations, and they want to collaborate, which is great, right? This is fantastic. Today, that will oftentimes be sharing credentials or having long-lived tokens or things like that, which is, as many security folks in the audience will report, a security nightmare. No matter how much auditing and things you do, good luck. So our woman in organization B, our data scientist, says, well, I'd like to get access to your data. And our person in organization A says, GDPR, right? Congratulations. You've now failed to move forward in any way. And she's very unhappy. So what would it look like to rethink this in a powerful way which didn't have the same security surface area? I'm not saying it's a panacea. There's still things to be thought through here. But you could think about this in what we're calling insulated jobs. And so for insulated jobs, what this looks like is you add Bacalhau into the destination organization, and it will have what we are calling security enclaves, secure enclaves. Now, these enclaves are going to be holders for inputs and outputs to your overall job, and it transforms the way that the person in organization B, our data scientist, gets access to the data. So now when she says, I would like to get access to your data, our SRE in security 1 says, no problem. Just submit your job to the queue, and we'll go from there. She says, she writes up her job, she makes sure it works, and says, off you go, and submits it into the security enclave. Now, the person in organization B says, well, okay, it's there, it hasn't run, I'm going to make sure that it runs properly. So she observes it. She makes sure that it looks good, it's not exfiltrating anything, everything's fairly straightforward. Networking is turned off, can only run in this constrained way against a very specific data set that was pre-approved. She said, looks good, and releases it, and then it runs locally inside those local machines against that local data. Okay? And this is all built into the Bacalhau network open source project, right? From there, the system finishes, and it pushes back results again back into that security or secure enclave. Now our SRE says, fine, this is good. I'm going to go observe that and audit the results, make sure that nothing is being exfilled, using automated tools to look for PII. There are many, many types of scanners out there to ensure that we're following the correct procedure. She says, looks good, and releases it back to secure program A. And this is all done with the network itself. There's no additional structure. There's no having to reprogram your language or anything like that. You're able to use the existing WASM, and Docker containers that we support, and all those raw language commands that compile that I mentioned earlier. And then we're proud to talk about a new feature that is not there yet, but is coming soon. I don't know. Ask these folks. Called OctoStore. And the idea behind OctoStore is you get to audit everything. Everything you see there transparently will be recorded. So here is the entire flow of all those jobs. You get to audit who submitted, what was submitted, who audited the job, what machines they ran on, what data was accessed, what the results were produced, who audited the results, and who downloaded. And that's all built in for free. Automatically, that recording goes on. All with unique content identifiers to ensure that that can never be changed because those hashes are generated automatically. And those are recorded and again, written permanently looking forward. So you may say, these sound like science projects. You can't possibly be doing things in the real world. That is wrong. You are lying. One of the ones that we're really excited about is a proof of concept we're going through with the city of Las Vegas right now. So today, the city of Las Vegas has about 15,000 cameras spread across many, many different divisions. They're producing, on the order of PIBs a day of video stream, and they're doing absolutely nothing with them. They have a real human being just watching the videos and calling it a day. That is not sustainable, and it's certainly not an efficient way to go forward. What they are going to do with Bacalhau is deploy VMs out to the edges of the network to run processing over those video streams, to create indexes on what's going on there using things like YOLO and other things like that to look at slip and falls or car accidents or, I don't know, the Batmobile, whatever, right? And out there, way out on the edge, touching the walker, you're out there and you're basically trying to figure out exactly what's going on as efficiently as you can. Because what you don't want to have happen is have that all stream in to that central location, having to deal with massive amount of storage and bandwidth and things like that. You'd like to push that directly to archival storage and keep that cheap and cheerful and only go back to those indexes when necessary. That's what we're in the process of working through with the city of Las Vegas. Things are going very well so far, and we're excited to expand that shortly. We're doing accelerated science with LabDAO. That's an effort to, again, collect a number of different components, a number of different data sources, help merge them and make them much more efficient. We're doing preliminary work with Caltech's High Energy Physics Lab. Again, organizations producing PIBs of data today and attempting not to push that to the center unless you see anomalies and things like that. And we're also doing some work with the Boeing Institute. Those are the folks behind the original SETI at Home and so on and so forth. And again, trying to do distributed computing where anyone can contribute their compute to this network in those public ways. Very excited to participate in that. And finally, WeatherXM is doing some tremendous stuff around forecasting accuracy, and we're really excited to contribute to that as well. Again, and what you're hearing over and over again is there are so many streams, so many data sets out there. What we're trying to do is make those data sets more useful as they are today, rather than transforming them, and particularly transforming the way that people are using those pipelines. And with that, that is the Bacalhau project. What you can see here is several QR codes. Eventually, I'm going to have a slide full of QR codes and no words. But you can see how to contact me there. All of this information and the network is publicly available today on bacalhau.org. You also have the Compute Over Data Working Group, where we try and collaborate with other folks interested in any form of distributed compute. We want to talk to you. That is a collaborative organization that is not led by me. It is all of us coming together. That's cod.cloud. And if you have any questions, you can reach out at Bacalhau, contact us. You can see the URL there and the QR code. And with that, I think I have about 2 minutes for questions.
Thank you very much. Brilliant. Right.
I don't know if I'm the only person who was quite slow in the room, but I eventually made the connection between compute over data,
yes,
COD, Bacalhau. I got there in the end.
Yes.
Right, who has questions?
Yeah. I can just repeat it if you want, Liz. Oh.
It's okay. I'm nearly there now. For the benefit of the stream.
So you mentioned folding at home, which is a very interesting kind of distributed compute project. But my understanding of that is, they'll send the data out, a problem that you want to solve, and then it's sent back into a central location. So. Yeah. I was thinking that sounds like a perfectly suitable application for what you're doing, but maybe even more suitable would be some data that you just happen to locally have. Could you just give a couple of other examples? Maybe people processing data from their Ring doorbells or something locally and sending it in.
IoT is killer, edge is killer. Basically, anytime your data is outstripping your necessary bandwidth to move things around, you're going to run into this, right? And gene sequencers that are producing PIBs of data in even over a 10 gigabit connection that would take a year to move. IoT in particular, things like temperature sensors spread around the globe, right? Often in a very, very limited bandwidth connection back, 256 kilobits and things like that. You're really going to want to do initial filtering and things like that at the edge. One of the things here is it's the distribution of compute rather than the necessarily the distribution of data. It's really both of those. We have a proof of concept right now to do eventing. So there's no data locally other than just the stream of, for example, a camera. coming in. And as that comes in, it's going to run over a window of a certain amount of time and tell you whether or not a human being is there. The moment that happens, it then runs the job. And again, that's run at the edge, just observing the local network and the local events. And the folding at home one is an example because yes, I'm not downloading a petabyte of data. It is up to the original. If they really want to take advantage of these things, they're going to need to shard the data already, right? And it's likely that they are, right? It's unlikely that you'll put a PIB of data on a single machine. You're probably sharding it in some way. And once you begin that sharding, then a job like that at folding at home, it would do a download of whatever, 100 megabytes, and you would do some work on that 100 megabytes, and then you pass back a partial result. And it'd be up to the person on the other end to reduce the result down and come back. But like I said, I like to say, if you have more than 20 machines or just more than 100 gigabytes of data, that's small, you're probably running into a problem that we can help you with today.
Thanks.
Unless anybody else puts up their hand, I'm going to ask a question myself. I saw a couple of references there to Filecoin and storing data in Filecoin. Is that a kind of an inherent part of the project, or is that kind of independent?
It is a parallel component of the project, but not required at all. So we support on-premises, we support non-Filecoin-based work. For those that don't know, Filecoin is a very successful network out there. It is the incentivization layer on top of IPFS. IPFS and Filecoin together have about 18 exabytes of stuff out there. So not a trivial amount of meaningful scientific and other public data. It is very specific types of data sets that go up there because today you have to manage your encryption and so on and so forth yourself. But they are very, very popular and used very broadly. That said, if I don't want to engage in the public network for some reason, then I might want to store the data myself or things like that. And so you do not need to connect at all to the public Filecoin network. IPFS is used, but it is used as an implementation detail. It is something that's internal to our network because it gives us terrific hashes and lets us very simply understand whether or not this data set is equivalent to that data set over there and how to schedule against the location of the data rather than just raw available compute or a name or something like that.
Great, thank you. Any last takers for a question? All right, round of applause. Thank you very much for wrapping up our track today.